Hello everyone, welcome to the lecture number 22 of this NPTEL lecture series on charging infrastructure. In this lecture, we will see the concept of pulse width modulation and how it will help in making sure the implementation of 3-phase AC to DC converter. We will study in this particular lecture. Now before starting that, let us recap some of the concepts we have studied in previous lectures. We have seen in detail about the boost converter based PFC converters, where we have seen its operation, we have seen the design, different design aspects, we have seen the small signal modeling, we have also seen the closed loop control of this converter, in which the control objectives were to maintain the output voltage or regulate the output voltage, at the same time achieving the unity power factor current drawn from the AC source. And then we have seen its CCM operation, its DCM operation, and how these two operations are different and why these two operations, and when the two operations are used, how the controls will change, that we have seen in detail in some previous lectures. And then we have also seen how the PFC converter can be also obtained using flyback based converter, which is again a derived buck boost converter, or you can say that it has the same concept as the buck boost based converter. So we have also seen buck boost based PFC converters and its operation, and particularly the DCM operation of it, because during the DCM operation it acts as a voltage follower mode, or the effective input impedance of this converter is pure resistive, and thus the unity power factor current is being drawn from the AC voltage source. Now, having understood the single phase AC to DC converters, we now move our focus on 3-phase AC to DC converters. These single phase AC DC converters are used for low power applications going up to 7 kilowatt, but beyond that power level one need the 3-phase AC DC power converter. Now before starting the discussion on the 3-phase AC DC power converters, let us first understand the basic principal concept of pulse width modulation, which is one of the modulation method by which one achieves the AC to DC conversion for 3-phase systems, maintaining constant voltage at the output and having the unity power factor current drawn from the source. So let us understand the concept of the PWM, and before understanding the concept of PWM, we know that mostly we are dealing with voltage source converters, and in voltage source converter it is the half bridge configuration which is the fundamental building block, which can be using that half bridge one can actually build the buck converter, boost converter, buck boost converter, single phase AC DC converter, 3-phase AC DC converter, single phase DC AC converter, and 3-phase DC AC converter. It comprises of two switches, S1 and S2, and these are connected in a, I have shown in this manner. Now these switches, as we have seen, this both S1 and S2 blocks the voltage of one polarity and allows the current to flow through it in either direction. So this S1 and S2 blocks voltage of single polarity and allows current in either direction. So any switch which can support this kind of functionality can be used to realize this S1 and S2. It could be MOSFET with a body diode, or it could be the IGBT with freewheeling diode, or it could be BJT with freewheeling diode, or the, but mostly it is done using MOSFETs and IGBT with freewheeling diodes. Now if you see its operation, so it has two states, state 1 and state 2, or state A and state B. Let us give as state A and state B. In state A, my S1 switch is on, that is when you will see the S1 switch is on and S2 switch is off. Now since my S1 switch is on, S2 switch is off, what happens is that this entire VDC will come across this point, this, so S2 blocks VDC voltage. When the S1 is on, it carries the current depending upon the load, I mean if the load is having current in this direction, it will draw current in this direction. If the load is having current in this direction, the S1 has to allow current to flow in this direction. Now if you look very carefully, here we have resistive load and a large inductor is kept at the pole of half bridge, which is the standard configuration one can have in any voltage source converter, whether it is AC to DC, DC to AC or DC to DC converter, where the inductor is placed at the pole of the half bridge. Now this half bridge configuration, irrespective of the direction of load current, can impose voltage at its pole having magnitude same as that of the voltage source. So in this, when the S1 is on and S2 is off, what happens is that the voltage across VAO, the voltage across VAO is nothing but VDC by 2, and this, you can say, this point or this midpoint of these two switches are also called as a pole of the half bridge, and the voltage VAO is actually called as the pole voltage. That means the voltage which is appearing at VA to O, that is the pole voltage. Now the pole voltage is VDC by 2, and if we see the VAN, where N is the negative terminal of the DC link, is nothing but VAN is nothing but VDC, and it actually appears across switch S2. Now if we take the next state, if we just see the next stage, in next stage, let me write this one on here, pole of the half bridge. Now if we see the next stage, in next state, state B, what we are doing is we are turning off this switch S1 and we are allowing the switch S2, I mean, and you are turning on the switch S2. Now when you turn on the switch S2, you are actually applying the pole voltage, which is the voltage between VAO, nothing but minus VDC by 2. So at so in state A we were applying VDC by 2, in state B we are applying minus VDC by 2. And if you look very carefully, since my S2 switch is on, the voltage between A and N is actually 0, and that particular voltage is appearing across the S1. So S1 blocks the voltage of VDC in with this polarity, because always the VDC will be of this polarity. So S1 always block the voltage of this polarity. However, depending upon the load, let us say if the switch S2 is MOSFET, current is going from source to drain or from drain to source, depending upon the load or the magnitude of the inductance and resistance. So there could be possibility that there could be negative, I mean current going in this direction or in this direction in some portion of the line cycle. So irrespective of the load current, both S1 and S2 is blocking the voltage VDC, and it can allow current in either direction. It has to be realized in such a manner that both the switches can allow the current to flow in either directions. Now if you look very carefully, from the pole voltage, that means VAO, we are applying VDC by 2 for some time whenever my S1 is on, and we are applying minus VDC by 2 for some time when my S2 is on. So we can actually vary the duration of this turn on time of S1 and S2, and that is when we can get the average pole voltage variation varying somewhere between minus VDC by 2 to plus VDC by 2, and that is how we can get from the DC we can get the AC output or AC at its output, or let us say if we have the AC at the output, we can actually generate the DC accordingly, vice versa in either direction. So let us see how this half bridge configuration, I mean we can vary this average pole voltage variation. Now for to do that, a very commonly used modulation technique which is called as a pulse width modulation is being used, where the output voltage of inverter, which is nothing but the pole voltage, the output voltage of the inverter is controlled by changing the width of the pole voltage VAO. So if we see the VAO for some time it is varying for VDC by 2, for some time it is having the minus VDC by 2. Now, if we vary the pulse width, that means we are not changing the magnitude, we are just changing the duration for which VDC by 2 is applied and minus VDC by 2 is applied. That means we are just changing the width of the pulses which is varying between VDC by 2 and minus VDC by 2. So, if we can change the timing or if we can change the duration of that switching pulses between VDC by 2 and minus VDC by 2, that means when if we change the width of the pole voltage VAO, then we can say that we are actually changing the pulse width, and that is why it is called as the pulse width modulation. Now, the simplest way of doing it is we can have the high frequency carrier signal. A high frequency carrier signal, it could be a triangle, it could be the ramp. Let us take a simple triangle signal which goes from plus Vc to minus Vc and then going from minus Vc to plus Vc in this one carrier cycle. So, if we see this carrier cycle and then again this pulse actually repeats itself, if we see it repeats itself like this, going from here, going like this, going from here and going like this. So, it repeats itself in one carrier cycle, it goes from plus Vc to minus Vc and then minus Vc to plus Vc. Now, if we see we have one high frequency carrier, we are taking high frequency carrier, that means the variation of this modulating signal is or the frequency of variation of this modulating signal is very small as compared to the frequency of this carrier signal. That means the time period during which the modulation signal changes is very much larger as compared to the value Tc. So, now if this modulating signal, which is, since the variation of this modulating signal is very slow, or you can say the time after which that variation or the change in the modulating signal will take place is very large as compared to Tc. So, in one Tc or in one carrier cycle, you can see that this modulating signal is kind of a constant. Now, this high frequency carrier is compared with low frequency modulating signal. Modulating signal, it is sometimes also called as a reference signal. And the low frequency modulating signal, I mean that low frequency modulating signal could be DC, where the frequency is equals to 0, or a sinusoidal with frequency very less than the carrier frequency, which is the case, you know, we have seen in case of boost PFC, we were doing the switching frequency very much larger than the line frequency. So, if we can ensure that this modulating signal is varying, you know, sinusoidally and having the frequency very much lesser than the carrier frequency, then we can try to implement this pulse width modulation. So, let us see how this can be implemented. Now, for example, here we see that we have a carrier which is varying between Vc to minus Vc, having a time period Tc, which is nothing but given by 1 by Fc, and where Fc is nothing but the carrier frequency, and this frequency is very much greater than the modulating signal frequency, and this modulating signal could be DC or could be a low frequency AC, which actually, since it is a low frequency signal or low frequency AC, it is having a constant magnitude or constant value over one carrier cycle Tc. Now, if we see very carefully, now in the half bridge configuration we can do a simple logic, since we are comparing this modulating signal with this carrier signal. What we can do, we can apply one logic where, I mean, again you can also apply the logic in a different manner also. In this particular method we are saying the switching logic could be, if my modulating wave, which is this modulating wave or modulating signal, if my modulating signal is greater than the carrier signal, which is this carrier signal, if my modulating wave is greater than the carrier, then I will turn on this top switch S1, which is here, top switch S1, and when the top switch S1 is on, we are applying VDC by 2 across the load, or you can say the pore voltage of this half bridge is nothing but VDC by 2. Otherwise, that means when the modulation wave is less than carrier wave, my S2 switch is on, and then we are applying minus VDC by 2 voltage across the load, or you can say the pole voltage of this half bridge. Now because of that, we see that if you see this particular part, only this particular part, in this particular part from the carrier is going from A to C, while my modulating wave or modulating signal is kept at constant at point B. So at that point from A to C point, what is happening is that my triangle signal or my carrier is greater than the modulating signal, and that is when my S2 switch is on, and that is when I am applying minus VDC by 2 across VAO. So you can see here it is minus VDC by 2, it is being applied. From C to E, we can say that our modulating signal, which is maintained at constant value at Vm, at this point my modulating wave is greater than the carrier wave, and that is when my S1 switch is on and I am applying VDC by 2 across VAO. Then again at that point we see that during this point we see that the value of the carrier wave is greater than the value of the modulating signal. That is when the second condition holds true, and then you are turning on the S2 switch, and that is when you are applying minus VDC by 2. So now if we see very carefully, if we try to apply the slope of line AC, if we see the slope of line AC, I mean line going from A to C, we can say that the slope we can write down nothing but this is at Vm and this is at Vc, is nothing but Vc minus Vm divided by, now if we look very carefully, this is Tc by 2 period, and this period is nothing but Tc by 2 minus T on. So we can write down this part from here to here. If this is T equal to 0, then this point is at Tc by 2 minus T on. So we can write this is at Vc and this is at this one. So we can say that slope of this line is nothing but Vc minus Vm, and this Vc was at 0, or we can say minus of Tc by 2 minus T on, that we can write. Similarly, we can also write slope of line AE is nothing but, it is going from Vc to minus Vc. So Vc minus Vc divided by, this is minus comes here, Tc by 2. Since it is having a negative slope, so this minus has been there, and that is when these two slopes are equal to each other. That means we can write slope of AC is equal to slope of AE, and that is when we can say that Vc minus Vm by Tc by 2 minus T on is nothing but 2 Vc, because this Vc minus becomes 2 times plus Vc divided by Tc by 2. And if we look very carefully, we can rearrange this particular term and we can rearrange this particular term to get Vm by 2 Vc, we can take it down here, plus 1 by 2 is nothing but equal to T on by Tc by 2. This we can get. We can also write here in this way. If we can rearrange this one here, now we can write like this: Vc minus Vm by 2 Vc, nothing but Tc by 2 minus T on by Tc by 2. Now that implies it is nothing but half minus Vm by 2 Vc 1 minus T on by Tc by 2, and this we can rearrange this particular part. So we can bring this side and this we can take this side. So it's Vm and 1 minus half, which is half. So we will get T on by Tc by 2, and this we can say this Vm by 2 Vc plus 1 by 2 equal to T on plus Tc by 2 is nothing but equal to D, which is nothing but nothing but D is nothing but the, we define a term called duty ratio, because it is the portion of Tc by 2 where your S1 switch is on. So, we can say this is nothing but a term called duty ratio. Now, let us define this as equation number 1, because we will be using this equation to derive the average pole voltage variation. Now, if we can do a simple thing, average pole voltage variation over a carrier cycle. So, this is my carrier cycle, Tc is a carrier cycle. We can say that we are applying minus VDC by 2 for Tc by 2 minus T on period, and we are applying VDC by 2. I mean, if we do only for Tc by 2, because the other part is also repeating itself, it is having a half wave symmetry around Tc by 2. If you look from Tc by 2, this side and this side both have the same variation. So, we can say that it has the half wave symmetry. So, we can write for Tc by 2 period, we can do the averaging up to Tc by 2 period, and that average will be the same average when we do the averaging up to Tc period. So, we will do minus VDC by 2, nothing but multiplied by Tc by 2 minus T on, plus VDC by 2 applied for T on period, and then over the Tc by 2 period averaging. So, when we do this particular term, will get reduced to VDC minus VDC by 2 plus VDC times T on by Tc by 2, and then when we rearrange it, will become minus VDC by 2 plus VDC times D value. Now, this D, how we can say D, because D is nothing but T on by Tc by 2, and then from the previous slide we will put this value of D, which is nothing but Vm by 2 Vc plus half, and we will put it over here, and when we will open this bracket, finally we will get average pole voltage variation, which is Va is nothing but equal to Vm by 2 Vc times Vdc. Now, Vdc is what? The DC link which you are applying, and Vm is what? Is the amplitude of your modulating signal. Means how far your modulating signal is away from this 0 line, and your Vc is nothing but the value up to which your carrier goes in one side, or you can say that the amplitude of your carrier signal. So, this is what we get. So, we can say that the average variation of pole voltage over a carrier cycle is proportional to the amplitude of this modulating signal sampled during the carrier cycle. We can say this one confidently, that if I sample this modulating signal which is varying slowly with respect to this carrier cycle, so we can say that the average pole voltage variation over the carrier cycle is proportional to the amplitude of modulating signal. Now, here we have taken two things. One is we assume that the modulating signal is constant in one carrier cycle, and if we look very carefully, my switches, if we say switches, here my switch S1 is on and here my switch S1 is off. So, we can say that here S1 is on and here S1 is off. Similarly, at this point my S2 is off and here again S2 is on. So, in one carrier cycle my switches changes its state, and that is when we can say that the carrier cycle in this particular scenario, when we are doing in this particular scenario, when we have this kind of carrier, we can say that the carrier cycle is nothing but equal to the switching cycle, and we can say that, we can also say that carrier frequency is nothing but equal to the switching frequency in this particular way of doing modulation. So, we have seen that the average pole voltage variation over the carrier cycle, which is also a switching cycle or switching period, we can say is proportional to the amplitude of the modulating signal, which is a constant value over that particular switching cycle or carrier cycle or switching period. Now, if I can vary, if you see this one, this amplitude of this modulating signal, if I can make sure if that amplitude varies sinusoidally, we can ensure that the average pole voltage variation over the switching cycle is also varies sinusoidally, and thus this kind of modulation is called as the sinusoidal pulse width modulation. And we can also see that this is the average pole voltage variation, but actually instantaneously the pole voltage has the pulses which is varying sinusoidally over the line cycle. So if my amplitude of this modulating wave varies sinusoidally, we can ensure that the width of the pole voltage pulses or the width of the pole voltage will also vary sinusoidally and switches between VDC by 2 and minus VDC by 2, and this is why it is called as the sinusoidal pulse width modulation, because the width of the pole voltage pulses are varying sinusoidally. And it is one of the commonly used high frequency pulse width modulation used in inverters to generate an AC voltage from a DC bus, or vice versa from AC voltage to a DC voltage, which is a very commonly used. We will study that as we go along. So here again the same concept we have done. We here whenever the modulating signal is greater than carrier signal, my S2 switch is on, and that is when it is applying plus VDC by 2, and when my carrier is greater than the modulating signal, my S2 switch is on, and that is when it is applying minus VDC by 2. Now here if you look very carefully, here we have taken the voltage with respect to the point O. Generally this point O does not exist, this is the fictitious reference point we have assumed, and this is also called as the fictitious midpoint. However, in actual scenario we have the point between A and N, and that is when if we see the variation which goes between A and N with this VDC by 2 added, constant DC added, we will see that it varies between 0 and VDC. So if we see the VAN voltage, VA capital N voltage, it is going between 0 and VDC voltage. Here it is going between VDC by 2 and minus VDC by 2. And again here if we see, if this modulating signal has the, let us say, frequency FM, and this carrier signal has the frequency FC, here we ensure that FC has to be very much greater than FM. This is the main criteria for this, because if we maintain that, then in each carrier cycle we ensure that the modulating signal is constant. Here you can see that there is variation, but just for the visual representation we have represented in this manner, but generally this carrier cycle is very much smaller. That is when we can ensure that we have the constant amplitude of the modulating signal. So we have already seen that if my Vm or the modulating voltage varies as Vm sin omega t, where omega is nothing but 2 pi Fm, and where Fm is nothing but frequency of the modulating signal, this is also called as the fundamental frequency, because this is a fundamental frequency with which the pulses of the pole voltages are varying. So that is why we call this modulating signal frequency as the fundamental frequency. And if we substitute this Vm in VAO average, which is nothing but Vm by 2 Vc times VDC, we will get that VAO, which is again varying with time, which is nothing but I mean that is varying with time, and this is VAO average. This is VAO averaged over the carrier cycle, is nothing but Vm sin omega t by 2 Vc into VDC. So thus we can ensure that if we vary our modulating signal by sinusoidally, we can also ensure that the average pole voltage variation over the carrier cycle also vary with the frequency same as that of the modulating signal. So if we look very carefully, this particular expression, we will define one term called as a modulation index, which is nothing but the ratio of peak of modulating signal, which is Vm, to the peak of the carrier signal, which is Vc. If we have seen that it goes between minus Vc to plus Vc, peak is Vc, and Vm is going, I mean is maximum going up to Vm value, as we have taken it is nothing but Vm sin omega t. So that will actually gives you, if we substitute this m value, we will get the average pole voltage variation over the carrier cycle or switching cycle is nothing but m VDC by 2 sin omega t. And this, if we see this pole voltage variation, shows that we have the fundamental component, which is having the frequency nothing but at Fm, and along with this it will also generate harmonics, because if you look very carefully, this is the actual pole voltage we are getting, VAO. The average of this pole voltage is nothing but, I mean the average of this pole voltage over the switching cycle is nothing but varying sinusoidally, but actually the voltage pulses or the voltages are varying between VDC by 2 and minus VDC by 2. So along with that fundamental frequency, we also have other harmonics which are also generated, as there is an error between the instantaneous applied voltage at the pole and the switching cycle averaged pole voltage. So if we look very carefully, when we have the sinusoidal pulse with variation, the output of that half bridge will have the fundamental component and modulating signal frequency, which is FM, and the amplitude of that fundamental component is nothing but MVDC by 2, and it depends upon the modulation index. That means if we keep the peak of our modulating signal smaller, then we will get a smaller fundamental component, and if we keep the peak of the modulating signal higher, maximum up to Vc, we will get the higher fundamental component. That means the amplitude of the average pole voltage variation will be more as compared to when we have the smaller amplitude of the modulating signal. Now along with this fundamental component, it also generates the harmonics. Now again, to calculate, to quantify this harmonics, we require again the derivation of a double Fourier series, which we will avoid to do in this particular lecture series. One can easily go through the literatures to obtain that mathematical formulation of for that particular harmonic, at what frequency those harmonics are present. So however, but we will take the inference of that particular mathematical expression, which says that the along with this fundamental component, which is MVDC by 2, we also have a harmonics at a carrier frequency and its sideband, which is given by IMF plus minus J, where MF is nothing but the ratio of FC by FM, where FC is the carrier frequency and FM is the modulating wave frequency or modulating signal frequency. Now it says that if I is odd, then J has to be even, and if I is even, then J has to be odd, where that means my I if my I equal to 1, the J should be 0, 2, 4, 6, and if my I is equals to 2, the J should be 1, 3, 5, and these are the harmonic number around which your harmonic lies. So for example, if I take my modulating signal frequency to be equal to the line frequency equal to 50 hertz, and I take MF equal to 21, that means my carrier frequency FC is nothing but 21 times 50 hertz, which is somewhere around 1050 hertz. Then we will have the frequency component at the fundamental frequency, and we have H equal to 1. This is at the FM frequency, so same as the modulating signal frequency. That means we have the fundamental component, and along with that we have the frequency component at the side bands of the carrier frequency, which is I equal to 1 and J equal to 0. So that means H equal to 21. So we have H equal to 21. Then we will keep I equal to 1 and J equal to 2. So we will have 21 plus minus 2. So 21 plus minus 2 means 23 and 19. And then when we keep I equal to 1, which is again 21 and plus minus 4. So when we keep plus minus 4, so it is 25 and 17. So this is at I equal to 1, J equal to 0, I equal to 1, J equal to 0. This is at I equal to 1, J equal to 2. This is at I equal to 1, J equal to minus 2. This is at I equal to 1, J equal to 4. This is at I equal to 1, J equal to minus 4. Similarly, after this we will keep I equal to 2 when we keep I equal to 2, 2 into 21 42, and j we will keep 1, so plus minus 1, so it is 43 and 41. So here it is I equal to 2, j equal to 1, I equal to 2, j equal to minus 1, and then we have I equal to 2 and j plus minus j equal to 3, so plus minus 3, so it is I equal to 2, j equal to 3, and then we also have our 39, which is I equal to 2, j equal to minus 3, and this is I equal to 2, j equal to 5. So accordingly we will get the sidebands of carrier frequency components along with the fundamental component, which is at modulating signal frequency. So let us take an example where we have taken VDC equal to 400 volt, we have taken our modulation index 0.9, where modulation index is nothing but Vm by Vc, and our MF, which is Fc by Fm, is equals to 21, and we again take our Fm value to be equal to Fs to be equal to 50 hertz. When we take that, our Fc is nothing but 1050 hertz. So taking this value, we have done the simulation in MATLAB and the output is shown over here. And this is the actual your VAO look like, VAO voltage. So if we see the VAO voltage, it has the pulse width modulated pulses, which actually varies sinusoidally. And if we see the frequency components, we have at fundamental component, which is at 50 hertz, and that value we will get nothing but equal to 180. So how we can get 180? We have kept modulation index 0.9, so 0.9 times 400 divided by 2, we will get that 180 volt, and which we have also seen over here. So this component is nothing but 180. Here we have plotted with magnitude percent as a percentage of frequency. Similarly, we will see the next harmonic exists at, this is 21, this is at 19, this is at 23, because this is the MF and this is plus minus j plus minus 2, so 19 23, this is your 17, this is our 25. So what we will see is that this variation, first of all we will see that from this the fundamental, the other harmonic content is actually falling or decreases as the harmonic order increases approximately with a value 1 by harmonic order, and here between this and this also the magnitude decreases in this manner as shown here. However, one can get the exact variation or the harmonic content by doing the double Fourier transformations. And this one is at if we do this one, this is 41, this is 43, then we have 39, here we have at 45, so then 47, and this is 37. So this is the pole voltage variation which we see across the VAO, where O is the fictitious midpoint, and this VAO will have this frequency component. Now if you look very carefully, we have frequency component at fundamental frequency, which is at 50 hertz, and then we have the frequency in the side bands of the carrier frequency, and that carrier frequency is very much larger than the fundamental frequency. So if we keep our carrier frequency much higher, here we have shown with 21, let us take, if we keep our carrier frequency to, let us take a very high value, in case of low power converters we can keep that into more than 100 or more than 200 number. So when we keep that such a higher value, so we are pushing the harmonics after the fundamental. We want only fundamental component, we want to convert DC to AC or AC to DC. So we are only bothered about fundamental component, but along with fundamental we are also introducing harmonics, but this harmonic we can push it to very larger frequencies, and thus we can design the smaller filters to filter out those harmonics at a very high frequency, and we can easily design the filter, a low pass filter which allows only the fundamental component to go, while filtering out those harmonic which exist at a very far away from the fundamental component. If we take this MF much higher, then we will have the harmonics existed across, at that higher frequencies. If we keep our carrier frequencies to be very high, or we can say we keep our switching frequencies to be very high, we are pushing the harmonics to a very high frequencies, and that is when we can design a smaller filter to filter out those high frequency harmonics and only let the fundamental component to go through it. Now here we have discussed DC to AC operation. Similarly, the same thing will happen when we are doing from AC to DC operation. So in AC to DC operation, we are actually applying a fundamental component of AC and we wanted a DC. So the same concept, but we have to see from the other side, and we can easily implement this concept in the AC to DC converters. So in this thing we have understood the concept of pulse width modulation, where pulse width of the pole voltage varies, and that is why it is called as a pulse width modulation, and we can vary them in proportional to that of the amplitude of that modulating signal, and that is when we can get any average pole voltage variation, and that pole voltage variation could also be varying sinusoidally or could also be varying with different frequencies. And however, the one condition is we must ensure that the frequency of that modulating signal has to be very much smaller than the carrier signal frequency. Now we will use this concept and stabilize the concepts related to 3-phase AC to DC power conversion, relying on the same concept of pulse width modulation, and that we will study from the next lecture. Thank you very much for patiently listening to this lecture.